And welcome back as we continue our journey around the sun. Let's go ahead and take a look at how the sun can affect our space weather. So to kick this discussion off, let's first discuss one of the most famous events in solar history, which was the Carrington event. In early September of 1859, two amateur astronomers, including Richard Carrington in England, independently observed a solar flare. Now, this solar flare was followed by a significant solar storm reaching the region of Earth's magnetic field, which was soon overloaded with charged particles. Aurora activity and the northern lights were visible well beyond their normal locations, as far south as Hawaii and the Caribbean. Now, the glowing lights in the sky were so intense that some people reported getting up in the middle of the night, thinking it must be daylight. The 1859 solar storm also happened at a time when a new technology was beginning, the telegraph system. And, of course, being now wired to everybody, it allowed people to communicate and experience things that weren't able to happen before in history. So the charged particles that overwhelmed Earth's magnetic field descended toward our planet's surface and affected the wires of the telegraph system. In fact, sparks were seen coming out of exposed wires and out of the telegraph machines in system offices. So this was something that was unprecedented in our history. And of course, because we are now all communicating, it allowed people to report this event kind of almost in real time. So, what were the sources of this space weather? How did this happen? Well, three solar phenomena, coronal holes, solar flares, and coronal mass ejections, or CME, account for most of the space weather that we experience here on Earth. Coronal holes allow the solar wind to flow freely away from the sun, unhindered by solar magnetic fields. When the solar wind reaches Earth, it causes Earth's magnetosphere to contract and then expand after the solar wind passes by. Now, these changes can cause, usually mild, electromagnetic disturbances on the Earth. Now, much more serious are solar flares, which shower the upper atmosphere of Earth with X-rays, energetic particles, and intense ultraviolet radiation. The X-rays and ultraviolet radiation can actually ionize the atoms in Earth's upper atmosphere, and the free electrons can build up a charge on the surface of spacecraft and may actually damage their electronics. But, of course, the third type, coronal mass ejections, are probably the most dangerous. A coronal mass ejection is an erupting bubble of tens of millions of tons of gas blown away from the sun into space. When this bubble reaches Earth a few days after leaving the sun, it heats the ionosphere, which expands and it reaches further into space. Consequently, friction between the atmosphere and spacecraft will increase, dragging satellites into lower orbits. During a solar maximum, several satellites are actually brought to such a low altitude they can actually be destroyed by friction with the atmosphere. In fact, a lot of times that these satellites end up needing a correction. They actually have to be boosted back higher in order to prevent them from crashing down. Now, what about actually down here on the surface? What solar storm damage can happen? Well, disturbances in Earth's magnetic field can cause disruptions in communications, especially cell phone and wireless systems. Even if we go all the way back to the Carrington event, we can see back when we had telegraph systems, how a solar storm could affect things back then. In fact, disruptions can be expected to occur several times a year during solar maximum. Changes in Earth's magnetic field due to coronal mass ejections can also cause surges in power lines large enough to burn out transformers and cause major power outages. This has actually happened in history. It happened in Quebec once upon a time. Now, electrical outages due to CMEs are much more likely to occur in North America than in Europe, because North America is actually closer to Earth's magnetic pole, where the currents induced by coronal mass ejections are the strongest. So if you are living in a location closer to one of our magnetic poles, you are more likely to experience these kind of events. Now, besides changing the orbits of satellites, coronal mass ejections can also distort the signals that are sent by them. So the effects can be large enough to actually reduce things like the accuracy of GPS. And GPS has a certain threshold in order for them to remain accurate. And so if these GPS-derived positions are not accurate, they cannot meet the limits required for them to operate effectively. Now, advanced warning of solar storms would help us minimize their disruptive effects. That, it's just like, weather here on Earth. The sooner we can know about it, the sooner we can take action. Things like power networks could be run at less than their full capacity, so they could absorb the effect of power surges. Communication networks could be prepared for malfunctions and have backup plans in space. Spacewalks could be timed to avoid major solar outbursts and prevent exposing any astronauts to the increased amount of solar radiation. So scientists are now trying to find ways to predict where and when flares and coronal mass ejections will occur, and whether they will either be big, fast events or small, slow ones with little consequence for Earth. Now, the strategy currently is to relate changes in the appearance of small active regions and changes in local magnetic fields on the Sun to that of subsequent eruptions. Now, one last thing to kind of talk about is Earth's climate and the sunspot cycle. Now, when the sun rises faithfully every day at a time that we can calculate precisely, scientists have determined that the sun's energy output is actually not truly consistent, but actually has varied over the centuries by a small amount, about less than 1%. And we've seen that the number of sunspots varies with the time between sunspot maximum of about 11 years, and the number of sunspots at maximum is not always the same. Considerable evidence actually shows us that between the years of 1645 and 1715, the number of sunspots, even at sunspot maximum, was actually much lower than it currently is now. Now, this interval of significantly low sunspot numbers was first noticed by Gustav Sweer in 1887 and then by E.W. Maunder in 1890, which we now call the Maunder minimum. Now, when the number of sunspots is high, the sun is, of course, active in various other ways as well. And as we might expect, some of this activity is going to affect Earth directly. For example, one of the things that happens is we get much more aurora displays when the sunspot number is high. More solar activity means more chances to disrupt the ionosphere, resulting in more auroras. Now, auroras are, of course, caused when energetically charged particles from the sun interact with Earth's magnetosphere, and the sun is more likely to spew out particles when it's active and the sunspot number is high. Historical accounts also indicate that auroral activity was abnormally low throughout several decades of the Maunder minimum. Now, the Maunder minimum was a time of exceptionally low temperatures also in Europe. It's sometimes referred to as the Little Ice Age. Now, one must be cautious, though, about assuming that low sunspot numbers or variations in the sun's output caused the Little Ice Age. Because one of the things we know is there's no satisfactory model that can really explain how reduction in solar activity might cause cooler temperatures here on Earth. In fact, it's even theorized that the Little Ice Age wasn't actually caused by anything solar, but it was actually probably more likely a result of volcanic activity.